Welcome to my video. My name is Ling Guo. I'm a PhD candidate from University of Oklahoma. Today, I'm briefing you how and why do satisficing strategy outperform optimal strategy in engineering design problems. Here, we define satisficing strategy is reached through compromise decision support problems, and cDSP for short, adaptive linear programming algorithms, and ALP for short, and decision support in the design of engineering systems, DSIDES for short. And the optimal strategy, there are a lot of them, but today we choose mathematical programming with the different methods in SciPy, a package in Python. First, we choose a test problem with two nonlinear objectives and two variables and upper and lower bounds of the variables, and we use weight to combine the two objectives. So the problem is with nonlinear equations and multi-objectives, and we visualize the two objectives on the right-hand side. They are nonlinear, but they are convex. So we want to maximize the two objectives. We convert this problem into a compromise DSP and cDSP for short. Because we identify the first objective can never exceed 14, so we use 14 as its target. And the second objective can never exceed 8, and we use 8 as its objective, target. And we use a deviation variable of each goal we minimize these deviation variables here to make sure we achieve the two goals as best as we can. And the deviation variables have minus and plus. The D minus means underachievement of a goal, and D plus means overachievement. We can minimize both of them to reach the target exactly, not more and not less. And pay attention that we can only have one of the two deviation variables be a positive value, and the other one must be 0. Of course, because a goal can either underachieved or overachieved or exactly achieved. It can not both underachieved and overachieved. And given that, we formulate the cDSP and solve it using ALP. And then for the mathematical programming, we use Python. But a lot of methods in Python required no constraint or Jacobian matrix. Only these three happen to solve this problem and give a feasible solution. So we use ALP to compare with these three algorithms. Here is the result. We use 5 weight scenarios or weight vectors to combine the two objectives differently. And for each weight scenario, we use different starting point, and because we know that those starting point are vertex point, so we just use them here. The starting point is important because the algorithms linearize the problem to a linear problem around this starting point, so it can seriously affect the linearization and the solution. And for each of these 4 algorithms, we use 2 columns to visualize the solution point and the corresponding goal achievement value. And I highlight the dominated solutions in red. We observe that all of these algorithms may return dominated solutions. Some may return more than others. And the first 3 algorithms in Python are sensitive to the starting point. When we change the starting point, the results sometimes change. But ALP is insensitive to starting point. And I'll give you the reason later. But for ALP, there's one scenario that we are also sticking to the local minimum, the local optimum, because we linearize the problem around the starting point, and any linearization is an approximation that may surrender the accuracy of the problem, so we may not reach the global optimum, but anyway, it's good enough and it's feasible. And we visualize the solutions using a 2-dimension objective space. The horizontal axis is the value of the first objective, and the horizontal one, the vertical one is the second. We want to maximize both of the objectives, so we want to achieve the solution point to be here on the upright corner. And we can observe that they are all same for this simple problem. The observation is that ALP can manage constraints, and it does not have to have Jacobian matrix to solve the problem. And we also have a explore module that we can do a interior point searching to return a relatively good starting point. That's why the results are insensitive to starting point changing. And sometimes using ALP may also return local optimum, but although its local optimum is still good enough, which is more desired in engineering design. And all of the 4 algorithms here we use return the results meeting the necessary Kohn-Tucker conditions or KKT conditions, but not the sufficient KKT conditions. This allows the results to be good enough and relatively robust to uncertainties, because the more conditions we meet, anything happen to the problem, any uncertainty takes place may break these conditions and we may lose the solutions. That's why we desire only meeting the necessary Kohn-Tucker condition. And next, we try another test problem. So this problem has non-convexity here, and we visualize the 2 objectives here. We can see the non-convexity here. And we convert it into cDSP. This time we identify the target of the goal one is 1.2. That's the only thing change versus problem 1. And implementing the problem and see the results that COBYLA cannot manage bounds for non-convex problem. And the trust constraint and SLSQP sometimes cannot return a feasible solution for these ones with a hyphen in it. Are some solutions either violate constraints or bounds, or no solutions at all. But ALP again can always return a feasible solution and insensitive to starting point, and most of the time good enough. Sometimes SLSQP can return better results than ALP, but it depends on its starting point. We visualize the solutions to the problem using 3 different algorithms. Again, we desire the upright corner to be the utopian point. So here is the observation. Using trust constraint, the feasibility is sensitive to starting point, and it's relatively satisfying. Using SLSQP, the feasibility is sensitive to starting point, and the result is not satisfying because the points are not to the upright corner. And using ALP, the results is better because first of all, it's insensitive to starting point. We do not need any domain knowledge to set a starting point to a good point and then start solving the problem. And also it's good enough and it's diverse. Every time it can return a feasible solution. But for these 2 previous algorithms, sometimes it cannot return feasible solution. So using cDSP, ALP, and DSIDES, the engineers can formulate and explore the engineering design problems with nonlinear equations, multiple objectives, and non-convex solution space, because a lot of engineering design problems are non-convex. The benefits of using cDSP, ALP, and DSIDES are the feasibility of the solution is robust to starting point, the diversity of the solution is relatively good, and the optimality, or in other words, completion of the goals, is relatively robust to the starting point, singularity of Jacobian matrix, and the local gradient of the starting point. So anyway, for engineering design problems, satisficing strategy is much desired. And then we tested third problem with different scaling of the two objectives. So we simply multiply the second objective by 50 to make the units of the two objectives different, to see if one objective dominates the other and they cannot reach a feasible solution. So we manage one more complexity, that is the objectives with various units or different scale. We visualize the two objectives, and the achieved value of the objectives vary a lot. For the first objective, it's never exceed 1. For the second, it's from minus 600 to the positive 400. So it's a very interesting design problem. We add 2 more constraints to make sure the two objectives are positive and convert them into cDSP, and we observe the target of the second goal should be 400. And by implementing the problem, we see that none of the first 3 algorithms in Python, in SciPy, can solve this problem. They either violate one or more constraints or bounds, or simply cannot return a feasible solution. But for ALP, it can always return a feasible solution with relatively good enough goal achievement. So we visualize ALP's result using this 2-dimension objective space, and we see it's very diverse among the solutions. The feasibility and goal completion are insensitive to starting point again, and goals do not dominate each other due to the unit variation. And the diversity we can observe, each goal can drive the solution to a different trajectory regardless of the nonconvexity of the feasible solution space. So from test problem 3, we can further observe that the objectives with different units can be managed using cDSP, and more benefits using cDSP that I do not cover in this talk, but I will introduce in later talks. When the problem is coupled decision problem, which means we have both discrete variables and continuous variables, and in optimization it's named mixed integer programming. But for cDSP, because of its benefit of managing the previous complexities, it can outperform mixed integer programming. And when using the comprehensive form of Archimedean and preemptive, or in other words, the scalarization of the goal objectives or the priority of the objectives, we can further observe the benefits of using cDSP, using these 2 strategies and the combination of the 2 strategies. And when the number of constraints exceeds the number of the variables, which also happens in engineering design, because in engineering design, more often than not, we face that we can only leverage very minimum number of variables, but we need to satisfy a lot of requirements. That's why the coefficient matrix, it's a thin and long one. So in that problem, we cannot solve it using simplex. In DSIDES, we solve it using dual simplex, which also is a benefit. And finally, meeting only the necessary contact conditions but not the sufficient one make the solution good enough but robust to uncertainties. So why? Here I briefly introduce why, and in the next video I will introduce them in details. Using cDSP, we minimize the deviation variables d plus and d minus, so the Lagrange equation does not depend on decision variables x. What's the benefit? The variation of decision variables do not affect the feasibility of a solution, and scalarize the goals regardless of the unit difference, and multiple objectives can be managed. And also using ALP, we sequentially linearize the nonlinear constraint and non-convex equations. If the gradient of an equation is greater than minus 0.15, which means it's slightly non-convex, the equation is linearized around the starting point sequentially, and multiple linear constraints are used to substitute the one nonlinear equation. In this way, we can manage non-convex problem. And using do simplex, DSIDES can return a solution to a problem with more constraints than variables, which is quite desired in engineering design problem. And with explored module, DSIDES combine interior point searching and simplex to approach satisficing. I want to acknowledge my collaborators, Ru Wang and Yu Huang, and welcome to explore my webpage using this QR code. Thank you.